Imagine the early days of chemistry as an infinite, violently unorganized supermarket. You have dozens of raw metals and colored gases floating around, but there are absolutely no aisles or labels. By the mid-1800s, scientists had isolated over 60 individual elements. They knew these substances existed, but they had zero understanding of how they actually related to each other. Inside these crowded rooms of glassware and chemicals, early chemists desperately searched for order. Without a framework to predict how elements would behave, the science stalled. Finding a pattern in this chaos was the only way for chemistry to move past guesswork. Johann Döbereiner realized that when elements were grouped by similar traits, like lithium, sodium, and potassium, a mathematical link appeared. If you take the atomic weights of the outer two and calculate the average, you get the exact weight of the middle element. Later, John Newlands arranged the elements by weight and saw their physical properties repeat every eighth step, acting exactly like a musical scale. He called it the law of octaves. But both systems broke down. When chemists tried to apply these rules to elements with much higher atomic masses, the patterns collapsed. Nature was clearly operating on strict mathematical rules. Scientists were just looking at the wrong numbers. Then came Dmitri Mendeleev. He tried organizing all known elements into a grid, sorting them by ascending atomic weights and identical chemical properties. This is Mendeleev's grid. Instead of a strict sequence of weights, he prioritized chemical behavior, forcing him to leave empty spaces. For a gap below aluminum, he predicted Eka aluminum, calculating its exact weight, density, and how it bonds with oxygen. Years later, a new element was discovered, gallium. Its physical properties perfectly matched Mendeleev's calculations for that empty slot. Mendeleev proved the elements weren't a random collection of dust. They obeyed a hidden law of nature that could be used to identify elements before they were even found. But the matrix had a glitch. Tellurium is heavier than iodine, yet putting tellurium first was the only way to make their chemical properties align in the columns. The weight pattern was flawed. In 1913, Henry Moseley bypassed atomic weight entirely. Instead, he fired high-energy X-rays directly at the atoms. When struck, each element emitted a unique X-ray frequency. Moseley realized these frequencies corresponded exactly to a specific number of positive charges, protons, inside the nucleus. He called this the atomic number. By organizing the grid by proton count instead of weight, the anomalies vanished. Tellurium has 52 protons, and iodine has 53. Moseley proved that the layout of the elements is dictated entirely by the internal anatomy of the atom itself. This is the modern periodic table, forming a specific shape of 18 vertical columns, or groups, and 7 horizontal rows, called periods. An element's position is driven by its outermost electrons, which sort the table into 4 distinct blocks, S, P, D, and F. Elements in a vertical group share the exact same outer electron setup. This makes them distinct chemical families, like alkali metals or halogens, that react in near-identical ways. The physical shape of this chart is a literal map of quantum mechanics and the layout of electron behavior. Predictable physical patterns sweep across the board. Atomic radius visibly shrinks as you move right across a period and expands moving down a group. Ionization energy, the energy required to steal an electron, drops as you move down and spikes traveling left to right. We can even track electronegativity, an atom's tendency to pull electrons toward itself. This single metric reveals exactly how different elements will react and bond together. By identifying an element's coordinate on this grid, we can predict exactly how it will interact with anything else in the universe. The periodic table lets us look at the chaotic dust of creation and see a functional, mathematical map of every reaction possible.